Thanks everybody for coming to Experimental Math. Today we have Michael Kiessling, who will be telling us about the classical radiation reaction problem.
Thank you, Yuna. And also thank you, Doron. Too bad you can't be here, but definitely wish you a speedy recovery. Same for your wife, and hopefully see you soon. The classical radiation reaction problem is basically my favorite problem since I was a student, and I'm going to tell you what it is about. So the goal is really the microscopic classical foundations of relativistic physics. Okay, so what do we want? We want a well-posed and generally covariant joint initial value problem for the motion of massive charged point particles and the evolution of the electromagnetic and gravitational fields which they generate. So that's the goal. Basically the relativistic analog of what in the Newtonian world one can prove. Right? We have an atomistic perspective. There is a world with lots of point particles and they move. You have a law of motion. And they move in such a way that they give rise to the structures that we are interested in describing in physics. And this is a very hard problem. And well, today I make my life easier. I will say something about gravity in the last slide, but generally I will switch off gravity. As a mathematician, that's easy. You set G equal to 0. G is Newton's constant of gravity. And we look at the model. There are point particles, charges, and there are fields, electromagnetic fields, and we want to put together a well-posed theory that can be treated as an initial value problem. Now let me begin by telling you about what does not work, but which is in most textbooks, in particular in plasma physics books, you find that the equations are on this slide, and on the next slide they are often proposed to be the exact microscopic equations for a plasma when n is large, n is the number of particles, and then comes a disclaimer, they're just too difficult to solve, and then they get being approximated with heuristic arguments, and you get some effective equations that people work with. Now, what you see here is the familiar Maxwell-Lorentz field equations. These are two evolution equations for the magnetic induction field B and the electric field E. T means time, S means the space vector in 3 dimensions, so I'm using a foliation of space-time into Lorentz slices. And we have point charges. I'm summing over k, that means they have an index. They are located at qk as a function of time. S is again my space vector. So this is a Dirac delta measure. This is the velocity of the particle. E is the charge. And then you have constraint equations. That's the familiar, the divergence of the magnetic induction field vanishes, and the divergence of the electric field is the sum of the charges, the charge density. Sum over the charges times their locations, the delta measures. And so these constraints, if the initial data for the fields are chosen such that the constraints are satisfied initially, they will automatically propagate by these equations. So this is really only a constraint on the initial data. And there's nothing wrong with these equations as they stand, but you have to couple them to the motion. The relativistic equations of particle motion have been proposed by Einstein, Lorentz, and Poincare, roughly at the same time. And what you see here is a statement that the velocity of a particle, the time derivative of position, of course, is 1 over the mass times the momentum divided by square root of 1 plus the square of the momentum, and then there's a square. You can see the speed of light is 1 in my lecture here. So that is a relation that Newton didn't know about. For Newton, this was without the square root. But Newton's law for the rate of change of momentum is still being used, right? Rate of change with respect to time is the force. And then comes Mr. Lorentz, and Lorentz tells you that the force on a point charge, given the electric and magnetic fields, is given by this expression, charge times, and then the sum of the electric field and the cross product of the velocity with the magnetic induction field, but evaluated at the position of the point charge. So that is basically the story. There's only one problem with that story. It makes no sense. So the problem is that these are symbolic equations, so that's something you would like to do that should look something like that. But if you take it literally, it makes no sense. And the reason is when you have point charges that are the sources of the electromagnetic fields, then the fields have a singularity exactly where the point charge is. But that's exactly where you have to evaluate the fields. Well, they don't exist where you have to evaluate them, so the force makes no sense. Yeah? And that's what I wrote here. The fields E and B are infinite in all directions, means they blow up, and the direction in which they point depends on from which direction you approach the point charge. You know? So that is what I mean by infinite in all directions. Now, typically people address this problem by averaging the fields over a neighborhood. Right? So that's already a little bit questionable. It's very popular, but the point is that why is it questionable? Because the result depends on how you do the averaging. So it's a result in convexity theory that says that for any vector between the extreme cases for any direction, there is a suitable averaging which can produce this. So that means somebody may hit the right averaging by chance, right? But a priori, if you don't have any particular good idea which averaging should be done, then it's pretty ambiguous. But worse, recently Deckard and Hartenstein showed that typically singularities will propagate from along the forward light cones of the initial positions of the particles, and as soon as another particle meets the forward initial light cone of another particle, right, then they meet the singularities there, and then the evolution breaks down. And I was only now talking about the force, the Lorentz force, from one particle onto another, not from one particle actually onto itself. So, moreover, there is no meaningful energy momentum conservation law that can be formulated if you have point sources, because the field's energy densities that one can write down, they are not integrable locally over any domain that contains the point charge. So this thing is completely infinite. And let me not get into what people have done to try to overcome it, but I will say later a little bit about that. The interesting thing is that roughly at the same time, Poincare already had some insights. Namely, these are generalized Maxwell equations. Actually, Maxwell wrote them down, except Maxwell didn't write these point charges, the moving point charges as source terms. That was something he didn't like. So for Maxwell, electromagnetism was a continuum theory, and he wanted to have continuum current density and charge density here. But these are the terms Lorentz then would write down. But now you actually have four fields, and they follow from mathematics. If you assume there are points that move, right, then the current density and the charge density together satisfy a continuity equation, and when you look at that, that looks like a four-dimensional divergence of a four-dimensional vector field. And from calculus, we all teach our students that in 3 dimensions, if you have a divergence-free vector field, then the vector field is the curl of yet another vector field. And that's the analog of that statement. The 4-dimensional divergence of these two blocks here vanishes. Therefore, you can write it even in a complex way. There are then fields B, D, E, and H, such that the charge density and current density can be written as linear combination of the first partial derivatives with respect to space and time of these fields in this combination. So this comes for free from mathematics. But you have too many fields and too few equations to make that by itself into field theory already. And what, however, is missing, therefore, is what people call the electromagnetic law of the vacuum, or what Maxwell called the law of the pure ether. He was thinking of electromagnetic waves propagating in the ether. And here's what Maxwell and also Mr. Lorentz chose the very simple H equals B and E equals D. Now it was long suspected already by Born-Infeld, definitely Born 1933, Born-Infeld 1934, that it is actually the Maxwell vacuum law which is the culprit. Remember, I just told you that the generalized Maxwell equations, they follow from mathematics if you just assume there are points that move through space. Right? That's something that comes for free, so you should not tamper with these equations. What does not follow from mathematics is how do you close them up, the closure relation, right, which I call the vacuum law here. So, if this causes trouble, why don't you try something else? Now, this looks, of course, not like a natural guess to generalize this simple law. Also, of course, how Born and Born-Infeld got there is a different story. This is very complicated, but in particular, it's non-linear and therefore makes progress very slow. In the 40s, Bopp first, and then Lande Thomas, and then finally Podolsky proposed a different law that is still linear, but is higher order derivatives to close up. And most of my talk will be about the electrodynamics you get when you replace Maxwell's law with the BLTP law. So first, just the field problem. So what is known? Well, for Maxwell-Lorentz, this is a pretty standard thing. They are linear, constant coefficient. If I give the motion of the charges, then I can solve the field Cauchy problem easily. For the Maxwell-Bopp, Lande Thomas, Podolsky problem, this is also pretty standard. It's a little bit higher order, more complicated expression, but again, it's linear PDEs with constant coefficients. Everything is fine. The really hard part is the Maxwell-Born-Infeld field equations because they are nonlinear, and global well-posedness was first proved without charges for small initial data by Gerald Speck, who was one of my PhD students here, and more recently Federico Pascalotto in Princeton generalized Speck's work to curved Schwarzschild space-time, that means outside of a black hole, and but there are no charges, right? Small data means you don't have point singularities that come from the charges. However, thanks to the nonlinearity, there is also the phenomenon of a finite time blow-up. It's not a shock that forms, right? But there's some blow-up of the energy density, but that is done for certain plane wave data, and that is not generic. So it's not known whether there is a generic neighborhood that does not have plane wave structure and leads to finite time blow-up. When you have point charges, then so far only the static problem has been nailed down, but there everything is then fine, so you do have only singularities at the point charge, you do not have other struts in particular that have been conjectured for a while to be there. And so that was done by myself, and also Bonheur et al. Worked on this. But now, the problem is how indeed we get to the forces. So these laws for the vacuum have the advantage that you do not have infinite field energies when you have a point charge. Well, for BLTP, that can be shown even with perfect dynamical scenarios. For Born-Infeld, so far only for static. So it's not really proven that that will be so. Also for dynamical scenarios that you do not have infinite field energies, but it's believed to be the case. But what about how do we get a hand on the forces? Remember, the Lorentz force formula was ill-defined because the fields don't exist where the point charge generates them. And that is still true here also. Even though the fields may not blow up, but they have a jump discontinuity in jumping in all directions, so you can still not evaluate this. So you need to do something else. And who came to the rescue is Mr. Poincare again, who also had suggested something that you will see a little bit later, for which one needs the field momentum. So I denote the field momentum with a Greek pi, okay, capital Pi here. And so for the Maxwell-Lorentz and for the Maxwell-Born-Infeld field equations, turns out that the field momentum is given by 1/4 pi times d cos b. Okay. For the MBLTP field equation, it becomes a monster. There is also d cos b, but then there is also e cos h minus e cos b, and then here's this Bopp parameter. There's one extra parameter in the model. The divergence of E times this funny combination of curl B and the partial time derivative of E. And it can be rigorously shown that this pi is locally integrable around any singularity, right, for the MBLTP fields. That was proven by myself and Shadi Tahvildar-Zadeh. And it is expected to be true for the Maxwell-Born-Infeld fields, but certainly false for the Maxwell-Lorentz fields. So that's an important ingredient. The field momentum is locally integral. And when the fields decay sufficiently rapidly at infinity, spatial infinity, it's globally integral. Namely, here's Poincare. Poincare proposed that instead of really the Lorentz force, we should work with such an expression. Namely, this would guarantee conservation of total momentum. This is a particle momentum. Take now a single particle. Time derivative of a momentum of a particle plus the time derivative of field momentum should be 0. So bring the field momentum to the other side, gets a minus sign, and so that should be the force that is acting on a particle if it participates in creating the fields that generate it. So now, okay, Poincare wrote that down, but what did he put in here? He put E cross B and used the Maxwell-Lorentz equation when everything is infinite. And then, instead of saying, but I found more general equations, let's change the vacuum law, he said, let's not use point charges. So that's one way of getting rid of the infinities, but now you have billiard balls, basically. And that's not a relativistically acceptable concept. You can regularize the problem this way, but that is what people then did. What normally is called Lorentz electrodynamics works actually with funny billiard balls and not with point particles, but here we say let's stick with the point particles, so we do not have to say what is the structure of a particle just here and not there. But we change the law of the vacuum, and of course I'm not proposing the law of the vacuum, I'm just using what others have proposed, in this case Bopp, Lande Thomas and Podolsky. So the interesting thing is, I will explain that when you do that, then with the BLTP law of the vacuum, then what do? You study the field equations for all kinds of possible motions that are compatible with the initial data for the given fields and for the particles. That means you get this here as a functional of all these generic motions. And it will depend on the generic position, momentum, and on the acceleration. Okay. Now, if you think of Mr. Newton, Newton was telling you that momentum is mass times acceleration. So here in special relativity, well, mass is then becoming a matrix, if you want, but that is linear in the acceleration here. And on the right side, there is a functional that is also depending on the acceleration. And the miracle that happens for BLTP electrodynamics is that this is a linear functional. It turns out to be a Volterra integral equation for the acceleration. That's what that is. So, you can then integrate this up formally and you get fixed point equations. If you can solve this, right, you stick wherever you see A in this expression there, and you will see that in the slides coming up. Then you get fixed point equations for Q and P. Right? The whole histories from the initial point on are mapped into themselves. And the point is that if this here is a Lifshitz map, then you are in business, then you have well-posedness. Here it is, theorem by myself and Shadi Tahvildar-Zadeh. BLTP electrodynamics is well-posed, well, locally, in time. We have a local well-posedness result. Important is that the so-called bare mass of a particle should not be 0. Global well-posedness follows if, in a finite amount of time, none of these three things happens. So no particle reaches the speed of light in finite time, no particle reaches an infinite acceleration, and no two particles approach to the same position, right? So, I mean, it's a little colloquially stated here. So that means if you can rule this out, you have global well-posedness. Now that hasn't been done, right? So, but locally it's fine. We have rigorously energy and momentum conservation. The self-force can be regularized. That means the radiation reaction feedback can be analyzed exactly. And that was also picked up by Wu Huang and Maria Radas from University of Texas in San Antonio. They studied one particle scattering in a given potential, and there is global well-posedness, and they studied the self-force effects in detail. There are some oddities in this theory, and that's actually why for quite a while I actually hesitated to work with it, because of these higher order derivatives. There are strange effects that we do not seem to be aware of in nature. Namely, it predicts longitudinal electrical waves without magnetic fields. Everybody learns electromagnetic waves are electromagnetic, and purely electrical waves don't exist in vacuum. This theory predicts there are. There are also subluminal transversal electromagnetic waves in addition to those that travel with the speed of light. Also not nice is that the field energy function is unbounded below. So in principle, a particle could borrow an arbitrarily negative field energy, right, to get itself an arbitrarily positive kinetic energy in a finite amount of time. So that is one of those things one cannot rule out a priori. And you have all these fields that require initial data. Normally, when you know B and D, let's say, then you have no freedom to choose also E and E dot. This theory demands to say something. So it is feasible, however, to map these into this by adding some postulate that you look only for field data that maximize the field energy given B and D. That means you want to make the field energy as little deep down negative as possible. No? So that's the idea, to stay away from that. But, all right. So let me talk about this Volterra equation. So I told you that from Newton, if there would not be the square root, you would have m times v is p, so therefore v is just 1 over m times p, but and then you take a derivative to get a, right? So now in relativity, because of the square root, this becomes a matrix, which is written down here, and I chose w to indicate an upside down m, like taking 1 over m, so to speak. This depends only on the momentum p again, on generic momentum. So acceleration is this matrix applied to this force. What is that? This is the vacuum force, which is just the Lorentz force, but for fields that do not contain a source. And then a source term. So where does that come from? We have linear field equations, PDEs, and we teach our students when you have a linear inhomogeneous equation, what do? You find a particular solution of the inhomogeneous equations, and then you add the general solution of the homogeneous one, and then you have the general solution. So basically that's what is behind this. So you do this, you take a particular solution with a point charge, let's say only one, and add the general solution without a point charge, and that gives two contributions. One is the familiar Lorentz force, but that D vac and E vac do not have singularities, so they are fine. But what is this piece? So and now comes the result of lots of hard work. Yeah, so you can call that the self-force, but it depends, of course, to some extent on your splitting on what you call the vacuum part. You can always add a vacuum part to the solution of the inhomogeneous equation, and it's still a solution to the inhomogeneous equations, right? And but anyway, let's call it the self-force. So this is the negative time derivative of pi computed only with the field that has the source. Now I need lots of space, so the first thing I do is I drop the superscript source. Now, I do funny trick to reduce the space integral to an integral over a ball of radius ct centered at the origin, not at the origin, at the original position of my point charge. So the reason you can do that is that the initial data are composed, say, if here's space, right, and we take time going upward, as people like to do in relativity theory, and then the particle may start here initially, having a certain velocity, so there is a certain slope to the trajectory it would take. Simply extend this into a straight line, also backward, and compute the corresponding electromagnetic field that corresponds to a boosted straight line motion of a particle. This is part of your initial data when you evaluate that field here at time t equals 0. And then you add to it some nice vacuum field without source. Now, what will happen, here's your forward light cone now. Alright, so. And the particle will move somehow, in some way, right? But given my initial data, and I take only the sourced field, right? So here I have just dropped source, but that means my vacuum field that is wobbling, this is already taken care of in the Lorentz force expression. So this is not showing up here. So that means outside I have basically the equivalent of a boosted field. So anything that changes will only change in here compared to the hypothetical straight line motion that corresponds to this boosted static field initially. So if I take the question, how does the time derivative of just this straight line motion, the electromagnetic field momentum that corresponds to this straight line motion, how does that change in time? The answer is not at all. It's 0. So I'm subtracting basically 0 from here. Then I notice by shifting this up here, right, I'm following just this, that the difference is actually 0 outside. So everything inside is what contributes, and that's what brings down the BCT. So now I have an integral over a finite region of space, and that can be evaluated. So now one splits this pi. Remember, pi was bilinear. Yeah? So when you look at the solution of the Maxwell, Bopp, Lande Thomas, Podolsky field equations, it comes in several terms. You can order them in terms of the strength of their singularity. There's a 1 over distance square singularity, a 1 over distance singularity in D and in H, right? And there's no infinity in E and B. And the combinations you look at is that also in pi, therefore, the worst singularity is simply 1 over distance square. And then there's a 1 over distance singularity and a term without a blow-up. So you sort that. Now that is actually what this sum over k here means. That is no singularity, 1 over distance square. So you have this sum of terms, but then you have a d over dt. So you bring that in, carry that out, and that gives you this long expression here. But I still haven't told you what the z is. The psi is just an abbreviation for the triple of q, v, and a. And this psi with a subscript 0 on top is just a hypothetical straight line auxiliary motion that just extends the initial velocity into a straight line. So, what is the z? The z is this. Brings in a new unknown. So, well, first of all, r stands for retarded time. We have to somehow evaluate these integrals, and what I'm doing is I'm foliating this in terms of, this is a ball, but I foliate the ball into spheres. But it's not concentric spheres, these are spheres that are centered at the retarded position. So they are all non-intersecting spheres, right? But not concentric. So that's a change of variable. N is just a unit normal vector on such a sphere, pointing to such a sphere. are these funny pies that one has to work out, and they are here. There is pi 0. Don't worry, I'm not going through this, just I want to point out you don't see any blue color in that formula. It's a long expression. Now we go one expression further, suddenly there's also pi 1, and pi 1 has the blue A, that's the acceleration, it only shows up in a linear form. And then finally there's also pi 2, again no blue. There's no acceleration in there. So that means the acceleration shows up only 4 times in these monsters, and then only in a linear fashion. And then, of course, you have the k's here. These are abbreviations for Bessel functions, Bessel function kernels that show up because of the Klein-Gordon operator that is actually in the BLTP law. So don't worry, I'm not going into the details. The most important part was just to show that you can work out all these details to get an explicit expression for the force, a monster. No? There are lots of integrals still to be done, but it's linear in the acceleration, and that gives you the linear Volterra integral equation for A. And that's the key proposition that indeed, under, as it is stated here, that under certain harmless assumption, this Volterra integral equation has a unique solution, and it depends Lifshitz continuously on the motion Q and P. And that's great, and that's it. The corollary of this is the well-posedness theorem. So that's the first time you see classical electrodynamics with point charges that is actually not only well defined but locally well posed. That means you continue uniquely into the future, not too far into the future, but it also depends Lifshitz continuously on the initial data only. But what does all this have to do with experimental mathematics and computers, right? Well, the computer entered, when you remember what I showed you was the cell force. No? I needed several pages just to write that damn thing down. Yeah? I'm not going to sit down and solve that by hand for any simple geometry, right? So you take Maple, and you program this for a simple test case, and I choose the litmus test. The litmus test is that following situation, that you take a constant electric field and place a charge at rest and release it and ask what happens. Now, the traditional theories that have been worked out of radiation reaction correction to the test charge motion, they all fail in this simple example. Yeah? They always give you a 0 radiation reaction force, even though the Larmor formula gives you that there's a lot of energy coming out from an accelerated particle, right? It's the square of the acceleration. Proportional to that is the power. And that should somehow have a feedback into the motion, but the formulas by Dirac, Landau, Lifshitz, Eliezer, Ford, O'Connell, they all vanish in this particular setup. So I asked, what happens here? Does this theory fail too? Should not, right? I mean, and it doesn't. So here's what Maple tells you. Yeah? So that's the velocity as a function of time. When the particle starts from 0 velocity, you release it at time t equals 0 in this constant electric field. And speed of light is 1, right? It's up there. And the green hatched curve is the test particle motion, and also identical to the motion you get from these models where either Landau and Lifshitz or Eliezer, Ford, O'Connell have added this radiation reaction correction term to the test particle expression, and it vanishes, and therefore they get just test particle motion. This here is what the BLTP tells you, and you see clearly that there is a delay in reaching the speed of light because of some kind of a friction term. The particle is converting some of the energy that the applied field delivers into its motion, it converts it into radiation coming out, and therefore it doesn't accelerate as much. Okay, that looks like expected, but then I did something, doing my own little experiments. I changed the strength of the electric field. I made it weaker. And I found that. And I thought, what the hell is this? So here, the test particle motion again, note that it's already 500, the other scale was 80 or so. So I go out to 500 units in time, And the test particle motion, whoosh, go up, right, reach the speed of light, I mean approaches it very closely. But in BLTP electrodynamics, the radiation friction means there is a terminal velocity. And then I chose some intermediate values and I found this. I thought, what is this? And then I was getting suspicious that Maple may actually do something funny here. Oh, but then you roll up the sleeves and then we were able to prove rigorously that this is not an artifact of numerics. So it was found using Maple because of some very complicated equation. But once you have an idea of what you are looking for, then you know what you try to prove. And it turns out that this is really not an artifact, and it can be understood in the following way. As I mentioned already, it's some kind of a radiation friction term. Yeah. And if the force is very small, the applied electric field strength is very small, it turns out that you can do the linear approximation for the friction force. And it becomes Newtonian friction. That is what we teach our students when we talk about simple differential equations. You drop a ball in the atmosphere, right, and you assume there is linear friction proportional to the velocity with a minus sign, and you reach a terminal velocity. And that's exactly what happens here. But if you make the electric field strength stronger and stronger, the terminal velocity keeps moving up, and it's no longer linear friction, it becomes nonlinear, but then there's a cutoff at some point. And if you push that over that cutoff, then you go to the speed of light. And the last picture that I had shown here is when you are just a little bit above that critical field strength, right? So the particle, the friction force is such that it basically cancels the applied field, but not exactly, so the particle reaches something that looks like an almost terminal velocity, but slowly you push it over the mountain, and then it picks up and goes there. And these are the only three possibilities that can happen here. So I promised I say something about also when gravity is not switched off. And so I would like to generalize what I have just presented here, which is special relativistic, to a general relativistic setting, but then you also get, of course, gravitational waves now into the story. There should be another radiation reaction feedback loop. And it turns out, I wrote here the genie is out of the bottle again, that to my surprise, even though the electromagnetic vacuum law has been changed and improved to the extent that you no longer have non-integrable field energy densities and momenta, this is not enough to get a well-posed joint initial value problem in general relativity. That was a surprise to me because many of the strange things that happen in general relativity, horrible space-time singularities when you couple Maxwell's equations, you get the idea that comes from the fact that you have a non-integrable energy momentum stress tensor coming from electromagnetism. And if that is your source term for the curvature of space-time, you shouldn't be surprised that you have also horrible singularities in the space-time then. So my expectation was that if you replace the vacuum law, the electromagnetic vacuum law, by something nice like BLTP or Born-Infeld, that would cure those horrible singularities. It turns out, to some extent, that is true, but only to some extent. And if you want to get a feedback loop from the gravitational, say, fields into the motion, then there's a big question mark here, and you get similar singularities like in the Lorentz electrodynamics, but now from the gravitational fields. So that indicates that you also have to change the coupling, the gravitational coupling, from space-time into the electromagnetic stress energy tensor. And so there's a joint work going on with Annegret Burtscher, John Stalker, and Shadi Tahvildar-Zadeh, where we are working on part of these problems. We need a second Bianchi identity in a weak form. Why? Because then you get basically this statement, which is usually interpreted as energy momentum conservation. Right? So it's a covariant derivative. But then the question is, does that now imply, like in the special relativistic case, the equation of motion? And as I said, you may have to change the gravitational coupling. So this is ongoing work, big project. And maybe in the future I can say something about that. But anyway, thanks, and here's some literature.
Do we have questions?
What's the effect of this kappa parameter?
The kappa parameter is the only new parameter in the world, so to speak, that Bopp introduced. It modifies the electromagnetic fields close to the point charges when they do not move rapidly or so. Say for static fields, for instance. So far away from the point charge, you just have the usual Coulomb field. When you get closer, then the deviation, 1 over kappa is the size over which the deviation becomes important. So
It's a smoothing scale?
it's like a smoothing scale, yes. But when you have dynamics, then things get different because, as I said, from this higher order derivatives that are there, it's not just a kappa, but you get new phenomena that, as far as I know, nobody has seen in nature, right? So that's why I never liked that theory. I worked on that in desperation because one infeld, which is actually, I like that more conceptually, is so hard. Right? And I wanted to make some progress. And so the linearity of the field equations offered that you can at least check your ideas, do they work? And it turns out, yes, they do work, so that makes you very confident that you're on the right track. And so, can one see this in nature? I don't know. Maybe nobody has really looked for it. Maybe the effect is small. Kappa should be really very big, actually, in order to be compatible, at least with some test cases where you know this is well tested in the lab. If kappa is small, you see effects coming out that definitely violate what our experiments say.
Thank your speaker again.